Alright, so this week we will get into, what is this? Chapter 7, yeah? Datums and datum targets. The slides we get from the, from the author is very difficult to handle since we have to make it easy to print for school. Yes, it's the alignments is so bad. But I believe they're readable. You can also download, alright, the original copies if you need it. They're like, it's just like very difficult to print. Yes. So anyway, here I make it a little bit better, yeah, if people want to print it. Alright, so let's get into this chapter. And here is the objective. I'm not going to read all of that. Yes. Of course, the datum. These are all the definition. You know, he make his slides like very. It's too much actually, but yes. Okay, so we'll get into the definition. When we say datum, we're talking about three things. All right, either point, line, or plane. Okay, we usually measure from one of these. Okay, and if you read it, you're not going to get it right away. Yeah, you don't have to remember all of them either. In our field, we have pocketbook, and some people make their own notes. Yeah, and it's really important if you want to keep in this line. Don't try to remember all of it. Yes. So if you get like datum is point, line, and plane, and we're going to measure something from them. All right, datum plane is just a flat surface, yeah. And you, since we're doing drawing, everything is right on your part features. Okay, you have your part. Part has many different kinds of features. Depends on the product, yeah. Depends on the model. And when you have to deal with producing, yeah, the model or the product that you draw, you need measurements to do it. Okay, and datum is really important to provide that measurement. And of course, we measure from a point, line, or plane. And here just a bragging about, oh, if that's a plane, that's a surface, yeah, it's a flat one. If that's a line, then that line thickness is 0, meaning like there's no thickness at all, just a regular line, yeah. And there's no variation. 0 variation means no variation, yeah, from the form of your part. The next thing that you need to know about datum is they're perfect, okay, in every respect, because we're measuring from them. If they're not perfect, yeah, there's no way you can be able to use them. So what can we do with that? We can, because of these measurements that we do from the datums, we can do production, yeah. We can do precision tools, processing, the equipment, so and so. And here is a list, and we use these tools to verify the accuracy, yeah, accuracy of the dimension that we do, and also of course dimension requirements for your parts. This is in another course, yeah, metrology, but of course you can just read it to know. So surface plates, machine tables, mandrels, and centering devices, diode indicators, gauge blocks, snap gauges, ring and plug gauges, so and so, all of them, we use them too, yeah, to check the dimensions in our parts. Then we're going to get into the very first one is your planar datum. So here we have an object, yeah, and there's a base of that object, and we call this one, look at this base, and that is your datum feature, and I give it like a letter A, yeah. And when you see this, you know that you're dealing with a datum. It can be a point, a line, or a plane, okay. Right now we're dealing with this base, so therefore that's a datum plane, yeah. And we give it the datum, this datum name is A, Yeah. So if somebody say datum A, you know that. If your sheet says go ahead and draw a datum A on this surface, then you should be able to do that using this symbol. Okay. So of course we can look at that, and this is our part, and here is your datum feature. Then we're gonna take a look at this datum simulator. Yeah, this is your simulated datum. This is our datum feature, and here is the simulated datum plane A, the one that we just saw, right? Right here. Okay. Of course, this drawing is kind of exaggerated one. Of course, when you see this, you know that we're exaggerating, yeah, the surface, so therefore it's definitely is not the perfect surface. You can see, you know, very big, like a big zoom to the surface that you saw just right now. Here looks like so perfect, but when you exaggerate it, we have some imperfections right in there on the surface. So here just comparing the regular datum feature and the datum simulator. Simulator means you're simulating it, making it, not real. So while we're doing the regular datum feature and the datum simulator, is in order for us to establish the datum plane A, okay, which is this one. It's very theoretical. You're gonna feel like, why do you have to do it? We just draw it, right? Of course, we're just explaining why we do that. It's because in order for you to just put that in there, first, yeah, here you can see right there, I can highlight it for you to establish, yeah, the datum plane A. We are going to think about the relationship between the feature and the simulator, yeah. So we go back to here, and that's what we're trying to do. Yeah. So while we're doing this, we first exaggerate it and then draw it, and then bring them together. That to datum plane. Yes. A got to be established between that datum feature and then your part and then your simulator. Yeah. This is all imagination, by the way. So you can be able to get this datum plane A. So we can be able to go back. Yeah, we can be able to put it like this, which is this little symbol is your datum feature symbol. Okay. So anyway, so that's just a theoretical thing behind it. Again, datums, all right, theoretical. And we assume exist. When we say theoretical, they don't exist, okay? Just the theories. Your actual measurements, your controls for your geometry features, all right? You cannot verify them from theoretical, right, entity. So you have to establish the datums in manufacturing and also in inspection processes. Yeah. So how do we do that? We're gonna bring the actual part features and we're gonna put that in contact with a simulated, all right, surface, like simulated tool or gauge surface. Only when you do that, you can process and inspect your equipment. Okay. Alright, now we get into the reference frame. So how are we going to put the datum reference frame all together? So you have about 3, okay, perpendicular planes, and that's going to give you your origin and also direction, yeah, to verify your dimension relationships. Again, this is very important for the quality people, yeah. My line is in quality. So when you do check, yeah, checking process, it's very important. So this is what it's saying, like verify, the process of verifying the measurement, right, is very much repeatable. You can do it again and again. And when you do it again and again, we use a different datum plane, okay? So that's what it's saying right here. So datum reference frame, we're gonna use it when you have more than one datum plane, yeah, to verify your measurements. So we're going to use that frame to verify the part dimensions. So what are you doing to verify the part dimensions? You make sure that the part, that part has been made to the specifications on your drawing. Okay, that's just a checking everything is okay in manufacturing. So measurement verification process, you do it. You're gonna bring in the datum features, and then you're gonna put it in contact with your appropriate datum simulator. So whatever you do on your drawing, like the one that we just showed, outside in the physical world, you're putting the gauge right on the datum feature. Physically is this, virtually or theoretically, we put it on the drawing. And that's what we do in verification. So outside features, you're gonna relate it, as written in your drawing, and you will go to the datum reference frame in your drawing to look at all the stuff that you need, to verify that dimensions requirements. The rest of them are just reiterating the same thing. If you get it, you use the tool against the datum feature on your part in order to verify the datum, reference frame, and then you're okay. So what are you verifying? You're verifying the dimension requirements, for manufacturing. So when you have a datum reference frame and you have to do the part measurements, what you're gonna do, you're gonna bring your datum feature against a simulator or datum simulator, together, and that's what you need to do. I have no idea why this author is repeating the same thing again and again either. I want to cut it out, but then we have to use this textbook slide. I try to get rid of it, the repeated stuff, but sometimes it just annoys me. I have no idea why he make it like so difficult to read. So basically saying like when you have the data reference frame, of course I'll show you, as we go into the chapter. So when you have this, you have three of them. So the very first one is your primary datum feature. Of course, all the datum feature, you definitely need to bring it in contact with your primary datum, from the datum reference frame. It is information, you have an information frame here, and you have three information right in that frame. You're going to take one out, and it's got to be in contact with your first feature. That's what it's saying, okay? And of course, I'll show you one by one. It's pretty easy. It's just like when you read it, it will bog you down a little bit. And of course, the way that he made it is with a lot of slides on it. Just, I think this is very old slides to animate, and he was using many different slides to go from slide to slide instead of animated on the same slide. Okay, probably he didn't know how to do the animation at that time, or animation feature wasn't there on PowerPoint at that time, I believe. Okay, whatever. So let's go into this. So here you can see a part, and then here in your drawing, in this drawing, of course, you can see the first datum plane, first main or primary, datum plane right there. So here you can be able to see the plane, right under the part. So you have one here. Also, there are other surfaces, see, So it depends on where you put it. Right here in this example, your primary datum plane is right here, almost on the bottom surface. Okay, again, this is already, he already wrote it on a few slides ago, so you can just ignore it. So I'll go into a secondary datum simulator. Again, you will do the same thing, So that's, you can get it from the datum reference frame. I said there are three of them, and second one, of course, we call it a secondary datum feature. So you're gonna call your secondary datum simulator, put them together, meaning like put it in contact between the datum feature and the secondary plane simulator. Yeah. And of course, whereas the secondary datum is going to be, it is going to be normal, which is 90-degree, yeah, to the primary datum. This is all you need to point, okay? The rest of them are the same, reiterating the same thing. Of course, so now we have secondary datum right there. See that? So when you visualize it, everything that you're reading here come into your head. Yeah. If you're reading here, all of this just confuse you, but don't feel bad about it. Yeah, it's gonna be okay. I'm going to make it easy for you. You have a part, and the very first plane is right at the bottom. The second plane got to be 90-degree to the first plane, which you can see this, and that's what is said normal. Yeah, so every time you say normal, the one plane is normal to the other plane, meaning it's making 90-degree, right, perpendicular to each other. Yeah, that's what it's saying. See that little 90-degree showing you? So now you get it, yeah, everything that clutter your mind, three previous slide. So anyway, so then let's go, and we're doing the same thing. We go to primary and then the secondary, of course, yeah. We will get into the tertiary data, the same thing. So we go one here, primary, secondary, and then you have your tertiary, which is this guy. See, that's also normal to the primary, see that, and normal to the secondary. So they're all normal to each other, meaning like they're all 90-degree to each other. Okay, so you get the idea of the three datum, yeah, planes that can be bring into connection with your part. So this is their all imagination right here. Yeah, it's in your mind. Of course, outside you, physical thing is only this one. That's what we call a datum. Yeah, simulated. A plane is because it is a datum simulator, because you're simulating it virtually inside of your head, imagining, oh, if that was it there. Of course, a physical outside, if you want to see the physical thing, you're going to have to bring another object. Yeah, so that's a couple of the first three slides is telling you to bring a gauge, yeah, and stick it right here on bottom surface, and in between them, when they are in contact, yeah, you get that plane. That's what it said. Yeah. So gauge me, it's just like a little block. Okay. So when you Google it, you're gonna see all the gauges right there. I don't have to show you these things. Yeah, you're already a adult and not high school students anymore. So therefore, every time you study, you can yes, open your internet. Everybody has the internet anyway, and you can look at, oh, what does she mean by gauge? Yeah, so open it, Google it, GAGE, put in, and you're gonna get thousands and thousands of images of gauge. Yeah, and put that into that. Right here, yeah. Since we don't have a physical lab here, I can show you what gauge is. Yeah, so this program is still developing, not like in the university. In university, of course, we have a big lab and we have all kinds of gauges that you can stick it to any part. Yeah, and so anyway, but we don't need a lab. Yeah, you have a brain which is more powerful than everything else in the whole world, you can imagine. So if you have a gauge, then you put that, yeah, right at that surface, and you're gonna get that. So anyway, the very important thing: three datum plane, primary, secondary, tertiary. The next important thing: they are perpendicular to each other. What is perpendicular? That's 90-degree to each other. Okay. In other words, we call it they are normal to each other. If you get it, I'll be very, very happy. So primary, you're having a contact 3 points. Secondary, you're having 2 points. Of course, the tertiary is the last one, so you have a 1 point contact. Yeah. So what are these points of contact? It's kind of like you're guarding the entire part, so the part won't move. So that's what it's saying. Simultaneously, to immobilize the part, you need 3 points of contact. Yeah, 1, and then 2, and then 3. For secondary, you have 2, and then tertiary, you have only 1. Yeah. Okay, so when we want to verify, we talk about the verification processes, measurement verification processes in a couple of slides in the beginning. Yeah. So when you want to verify the measurements, so what you do is your geometric controls. All right. They are relative to the datum feature plane. Yeah. And you have to verify by using, right, these datum plane. And that's what it's saying. Of course, datum plane, like I said, you measure stuff from there. Yeah. So when you do the verification of the measurement, you're checking if your measurement is all right, if your measurement is accurate. So all the measurements are yes, verified or draw from your plane, the datum plane. Okay. So therefore, of course, if you want to verify from here to here, yes, you are going to measure from this plane, of course. Yeah. So that's what it's talking about. If you want from here to here, because you select that plane. If you want, yeah, something else, then you also choose the plane that is in contact with that measurement, something else, okay? Okay, then we take the part out of it. So you are left with three planes. So they cross each other, yeah, and we call that cross a junction, intersection. And that intersection is going to be your axis of rotation. Yeah. So here, see, you can see this rotation symbol right there, meaning like the axis are when the two planes cross. Yeah. So here, here, and then here. And of course, all of your three axes, 1, 2, 3. Yeah. If you look continuously, yeah, to the end of it, you're gonna see. Look at that. The origin is right there. Yeah, meaning like they all cross at that point, and we call that the origin. Yeah, what is the origin? The origin is a point where all of your axes, yeah, cross, axis of rotation cross. Okay, and we already talked about it. All the planes are at 90 degrees to each other. We have a datum, yeah, simulated datum reference frame, and you're gonna establish it physically outside by using gauges. Yeah, already told you about that. Because if you don't bring the gauges, you can't be able to find that plane. Even though you know it is at the bottom of the surface, physically that plane doesn't exist. All you have is the part, right? The bottom surface. So in order for you to get that plane, you gotta bring another part and stick it into it. So the contact in between there it is. It's called, yeah, the simulated reference frame. Of course, in real life, your part, right? If you have like surfaces connected to each other, or you have adjacent part surfaces, you also have another tolerance, which is since surfaces make angle, yeah, in between them, you have another tolerance called the angular tolerance is also in there, and they will control their orientation, yeah, because the angle change can change the shape of that part. So it's not easy. Some people, like do like whatever in real life, in their job, and they think like doesn't really matter. But 1 degree change of the angle can cause a lot of disaster in your shape. When it comes to that, if that shape is very big, because you're not dealing only with a little tiny part like we do all the time in the academic world, at school. Of course, outside you have many different kinds of parts: small part, medium part, big part, and giant parts. So the degree change in between these connected surfaces or adjacent surfaces are very important. So therefore, the angular tolerance is also very important, and they will definitely control the orientation of that part respect to each other. So if you have like another tolerance, what we do, we usually put it in the note, in the drawing. And where can you find that? It's going to be on your engineering print drawing, You'll go all the way to the title block on your drawing, and you're going to see the tolerance of portions. So this is just a review for MET 101, And don't try to memorize everything. It is impossible for you at this level to be able to remember. Just get the pocketbook, okay, the one that I give you the name of it. In the syllabus, you have to buy that, okay? Everything, important points to do your drawing is right in there. So right now, just listen, and you will get it as you do your job. These are something that you can't be able to memorize, right? You have to do it because these are experience-based skills, Therefore, we force a student to use application without showing them, MET 101, 101 and 121, We make them do it, learn the application by yourself, force them. So by doing it, you kind of get it, okay? By reading, good luck, you will never get it. So I just try to tell you, like, if no geometric tolerance is going to apply to the angle dimension, yeah, and your angle control is we will deal with the size features MMC, the maximum material, yeah. And of course your rule review, and that's your rule number 1, yeah. We call that the envelope rule in the first couple of chapters. All right, so angular relationship, datums and the features. So how we have right here 1, yeah, a part right there, and here you can spot. Look at this, A and then B, yeah, and that's your datum feature. And the datum is right here plane, yeah. So datum plane A, datum plane B, right there for this part. Since they are plane, they are 90 degrees to each other, yeah, perfect. Shown right here. So what about the control? So how this angle is being controlled is your tolerances, yeah, and you can find it in your tolerance portion and your title block. Sometimes you can find it in the note, yeah. Sometimes you can find it in the feature control frames, yeah. Since you're dealing with the angle, so that's of course for your angularity. When you think about the relationship between this plane A and plane B, they are 90 degrees to each other, yeah. And the note is I'm talking about, that's right here. All right. And then here you can see the part, and we have 2 planes, yeah. And we're just telling you again, here you can see this is like a plus or minus, and we are giving you a tolerance specifications right there, yeah. Don't worry about the value right here. And every time you see something like this, you know that you're dealing with the angle, okay, dimension. So here angular dimensions, and since you see the plus or minus, you're dealing with the tolerance, yeah. So what is this? So what's so special about it? Because it's showing the relationship between the 2 datum feature, yeah. You have 2 datum features right here, which is A and B, yeah. And that relationship is the angle, because they are imaginary surfaces, yeah. So the relationship between the 2 surfaces or 2 planes is the angle. So we go to again your angular tolerances, and you're gonna see that, all right, the 2 surfaces got to be about this, yeah. You can of course vary in this range. Physical is going to be the surface bottom and the side surfaces, you know, of this part, yeah. You get it. And angle is the relationship between the 2 planes, okay. They can vary in that range. That's all you need to know, okay. Where can you find it? Tolerance. Therefore go to your title block. It's right in there, yeah. Now we're going to review and go all the way to your engineering drawing print right here, and we go to the title block, yeah. And here we go, your tolerance portions right there in this block. So that's your MET 101 review. Yes, we already did that. You should, okay. If you haven't, please take that course. And here angle is equal to plus or minus, yeah, 0 all the way to 30 degrees, which is same right there, okay. Now you can find the information right here. Where is it? It is in the title block. Where is the title block? In your engineering drawing, okay. Where it's in the tolerance portion, which is tolerance block or box, you can call it, okay. All right, now we're going to make it really big so you can see it, yeah. It's the same thing. You're dealing with the inches right here for this drawn. So this is where you can be able to find the tolerances, and of course these values are depends on your company, what they're doing, yeah, to design the product that they're manufacturing. So go with them. You don't have to do anything about it. Just follow everything they already have, okay. You only need to know where you can find the information, where you should put the information about the part that you're drawing or checking. Okay, then we go to the symbol. So the symbol is, you have already seen, you know, with the letter A, B, and then there is a square box, yeah. So That's what it's saying. You're going to use alphabetic letter or character, yeah, and you're going to attach that to your datum feature. So with a little triangle base with, and it looks like a little restaurant, yes, a waiting, yes, stand like that. And then you're going to stick it to your feature, where you want to specify the datum plane. So how are we going to attach it? We're going to use a leader, yes, in your drawing, and then you're going to terminate with a little stand, which is your triangle, and the triangle got to be filled, yeah. It's not an open triangle. You can leave it unfilled. These are just a drawing aspect. So now you're going to visualize it here. So that's what we're talking about. This triangle, this is filled, this is unfilled. You can leave it just like that, okay? And here is your letter or character, okay? And you're going to stick it to where you want the plane, okay, in your drawing to be. So here are examples on datum feature. Many different symbols. Then you got to get into the feature control frame. Control frame is nothing but it's just a little table like that, yeah. And you're gonna see primary and then secondary and then tertiary going A, B, C, yeah, in order. And of course, the whole thing is called the feature control frame. And these are your datum references. There are 3 of them, yeah, primary, secondary, and tertiary. So even though we put them in the box in order, but you can reference in any order you want, yeah. So that's what it's talking about here. And of course, any datum feature, yeah, you can reference in any order, and that order got to be based on your design function and also the feature relationship. Then we get into datum selection. How are we going to select them? Again, it's very bulky, but I'll just read one time for you. And then, of course, when you visualize, everything comes all together to you, yeah? So where are we going to use them? Datums are, we establish, yeah, to locate, to position, apart. So to check, of course, we do that to check the geometric tolerances because they're very important, okay? And these tolerances again are relative to your datum features. It's got to relate, otherwise it is impossible for you to measure. Again, datum features are there for you to measure from, okay? And of course, it's very good that way. So we can do the assembly, parts. We can do the specification, inspection, verifications, because we can be able to pinpoint the location, position, functional relationships, orientation of these parts, to each other. So your dimensional relationships. So these relationships exist between the datum features, on that part. And also your tolerance, features. They originate at the specified datum. So that's why datums are very important, okay? So when we select the datum feature, it's very important that we look at the feature size and then form, the part surface finish, right? These are very important factors to consider when we choose a datum feature. So where we're going to put the primary datum feature, we do it for locating or orienting the part in the assembly. So we will put the primary datum features to these parts, okay? Orientation function of your primary datum, we call it attitude control of the feature. Why? Because it is like a control of the entire feature, because you need them to locate the part in the assembly. Otherwise, you can't be able to find these parts in the assembly. Now we're going to select the datum features, and we will look at not only orientation, we're going to look at the design requirement function relationships, Why? Because your datum features are the features, and they determine the orientation, location, functional relationship of your part features. Of course, all these factors are dealing with the mating parts of these parts. The next thing is your feature size, form, finish, accessibility, everything about your part. They're important, yeah, in designing, manufacturing, and also verification process. So don't feel bad like when you're reading, it won't come to you in your mind right away. I told you every time, yeah, I lecture. It's all about the part, and your part has the size, your part has the form and shape, your part has the finish because it is made of some type of material, yeah, and the part always have features of some sort on them, okay. So when you do the designing or manufacturing or verifying, yes, because you have to verify what you manufacture if that's the way the manufactured product is what you have designed. You can't like make something which isn't what you design. Yeah, so therefore the verification is always checking the design and the manufactured parts or products and match or yes, accurate to each other. So so these are everything that you have for parts and products. Yeah, so it's gotta come naturally to you. Okay. And we gotta add the datum features to these features on the part in order for us to do the verification process. Yeah. Okay. Okay, here your feature in this example is holes. Yeah, and that gotta be located on the true position, meaning like the real position. And you have cylindrical tolerance zone is given to you here, one little diameter right there. I know that that's a cylindrical feature because these are the feature on that, yeah, on this part. And we can see it here, diameter. See, there is a little arrow right there pointing to this little circle right there and showing you that's 0.2 millimeters, okay? Of course, in this example, we know that it is millimeters right away because you can see the zero right in front of the decimal. Yeah, I'm not just reading this. We're reading this, okay? So in this control frames right here for you. And when you look at it, you spot the two datum here, the primary and secondary right there. And you spot it in your drawing. You can see right here and here they are, the surfaces are, yeah? Or plane you can see here, yes, and then that, of course. So the plane, this one is just a dimension right there, yeah? So here is the plane of this right there. Okay, and then come back to this control frame right there, and you see the maximum, see the MMC is right there. So since you're dealing with the MMC, you know that you have to get the smallest diameter. So the empty space got to be small in order for you to have the maximum material in your part, okay? And it is telling you your MMC is with secondary B, and the other one is your little right there, that, okay, hole, right, sides. Okay, there's nothing for this datum A, which is your primary datum, and that's your drawing specification. Okay, you've got 8 of them, right? These little holes right there, gotta follow that. Okay, hole is 0.2, that's your diameter for the circles. Okay, so when you look at your drawing, these things gonna come into your head right away just by looking at it. Yes, you know the control frame, you know the datum feature right there. You've got 2 of them. Primary, don't have to worry about any of it because there's no other description about it, just A. B has the MMC with it, so you know that this hole right there, got to be the smallest because you want material more on your part. Okay, then you gotta deal with this little feature right on that part, and it's that got to be 0.2, and of course we're gonna call MMC, so therefore I gotta make the hole as small as possible because I want the material on this part more max, okay, at its max. That gotta come into your head right away, and you have 8 of them by looking at it, and you have 2, your circles diameter is also given to you there. Okay. and that's just a circularity. Okay, now let's go to the next. This is just reiterating what I have just told you. So we go datum features, and then you go all the surfaces that locate and orient the part. Of course, you know that. And orientation of the part is determined by the surface A. Yes, because it's the control frame set it so. This frame is controlled, meaning like everything about that part is being controlled this way. It's talking to you that. So when you talk about this, oh, that's the orientation. It got to be orientation, because without that orientation, your part, okay, can never have this plane or relating to that surface. Okay. So orientation is got to be located because they are relative to each other. That two, okay, planes, this and that, 90 degree to each other. So that's how it being located and oriented. In order for that part to be oriented, this and this got to play together. They have a serious relationship, and that is 90 degree to each other. So when you do this plane and that plane 90 degree, yes, only imaginary surfaces connected to that part got to stand up right 90 degree, and you know that. Yes, because it said so. Hey, make this two plane 90 degree to each other, and that two planes are connected to the part, okay, in this way. Okay, the surface and then the surface, that surface and then this surface. This surface and then that surface is 90 degree. So when you set that up, your part is 90 degree. In that orientation, right? And then the next one is what I have already told you in the previous slide about the holes. Their dimension relative to your datums, of course. Why can you say that they're relative? Because they're controlled in that frame together. Put them all together. Therefore, when you see that this is controlled by this and this, you gotta know automatically, because you have two surfaces. What is it that controlling? It is controlling these holes. Okay, get it? And thus you should master the views by now. The front, and then this is of course side. So you can see the little holes right there. See that? Dion and Dion right there. Which is this and that, of course. Then this one is a mating part. Okay, for this part that we have just seen right here. Mating means they come into connect or get joined or connected. So how are we going to connect? We're going to clamp it in. So you have a mating part, and then this is all your original part. That's your mating part. How do we know? Because of this little, see, I am going fast. You gotta look slowly and carefully, and you're gonna see this edge right there. See, and of course, it will go into right this hole. So we call it the mating. We're gonna clamp it against. How we're gonna mate? We will clamp it in. Where? Because you're seeing this. See, that's why these function of these little tiny holes that we see right here is where all of your, okay, in this case it looks like a kind of like a bolt to me. Anyway, screw or bolt is going to go into these holes. 8 of them. Mating, we're clumping that two parts together by using this. Okay, and you have your surfaces, A, and then your another surface is B, 90 degree to each other. And of course this is bolt. So this is a bolt. The holes are right there, and your surface, A is going to be right here, which is, go back so you can see where the surface, this one, the vertical one, vertical one. So you know that that surface is going to come into right there, in between this. And that's your primary, and the secondary is 90 degree to that. It's got to be 90 degree, otherwise it's not going to fit to each other. So your diameter, B, it is a diameter. The surface datum is also B. Your diameter is also B. From here to here is the diameter of that circle right there. Okay, and that is going to position this part. So here you can see that that two parts are in assembly. Joining method is by using bolts, okay, into these holes. So therefore that dimension is very important, 0.2, otherwise your mating is not going to be successful. Okay. All right. So let's go in there. This is just trying to tell you what to be careful, when you do your drawing or inspection or verification. So your primary role performed by these datums, so what are we doing? We're establishing to verify the orientation, location, and functional relationship. You gotta get that, okay? In common word, it is fit gotta be successful. In order for the fit to be successful in your assembly, we use the datum to check the measurements are accurate. Otherwise, your bolt will not go into your hole, and the first part will not go into the second part circle, okay? You have your circle diameter, which are all holes anyway. So the holes gotta fit into each other. And of course, if you go to Walmart and buy some furniture, you're gonna see a lot of defects right in there. Some people are like, oh my god, producing some crap. So what are the problems? They have the datum verification problem right there, but they pass a quality check, so that means that someone is not doing, or someone is just deliberately throwing the product into the market. Who cares? So whatever money they get, they take it. Even though you do refund or whatever, the customer pay the money, and the company is getting that in that period. Okay, that's where they're making money. At least for that period, they make the money. So that's American business model. They don't care what the customer get, good product or qualified product or not. They just want to scoop that money in that period and make the most out of it. And then if they have to refund, you fund. If they have money, they refund. If they don't have money, they just go bankrupt and get rid of it. So try to get rich, shortest amount of way by throwing crap in the market is unfortunately most of the American business models. I hate to say that. Okay, but that is the world we're in right here. And because of blaming on each other, oh, that's a Chinese product. No, we're saying we actually the majority of the shareholders are from America. Doesn't matter where the factory is located, all over the world. It isn't the Chinese product. It's only made in China. Okay, made in China doesn't mean the Chinese people own these companies. The companies are owned by the rich countries, America, Europe, Canada, Australia, so and so. So people, who don't know, just saying all kinds of things that's not actually true outside. Okay, you're actually getting incredible amounts of labor costs, benefits, making serious profit. By sending or by outsourcing the factories in other people's country. We have, I believe, so many investors, so they're called international tycoons, and they own almost everywhere. And about, I think, 80% of the factories owned by the American businessmen. Man may not doesn't. I wasn't talking about me. It's just business people. So So the manufacturer, requirements. Again, you're gonna go back to the engineering document, and you will get all of it, everything that you need to know about the design information. And of course, we're studying the datum features right there, so you can also get the information of the datum features right in there. So you know like which surfaces should be specified as the datum feature. So when you do drafting, you're gonna put correctly the datum feature. And these surfaces that we give the datum features for, so surfaces that are designated as datum features, they are imperfect, in surface quality. Don't worry about this. It's just a daily thing right in there. Just concentrate on the symbols of the datum feature, your control frame, the information in the control frame. How are you gonna locate or orient? According to your three planes that are perpendicular to each other, you can be able to correctly orient your part. If you get that much, I'll be very, very happy. And your datum reference frame is very important, okay? And your drafter got to be quite sure that measurements, made from by using the information from your data reference frame. You can't do any kind of variations or defects. Okay, you have to strictly follow, because we call that, yes, reference frame. Reference meaning we refer to that information. Okay, sometimes you can even get the information of the surface finish right in there. So this is for the designer. Yeah, you have to think very hard before you establish this datum reference frame. You have to think about accuracy. You have to think about surface finish. Yeah, with your selected datum features. And then we'll get into the planar feature datums. Sometimes you only use a single datum, and that's sufficient, meaning like it's enough. Yeah, for verification. In that case, what you're going to do is your datum reference, yeah, is your primary datum, because you have. And here is another example. And you have a part, and here you have your control frame right there. Yeah, you're dealing with you can see parallel. Yeah, here is your parallelism right there. Okay, and here is your 0.4. And you have the datum. There's only one single, so that's your primary, and which is on the surface. Okay, right there. And of course your dimension, you can go from your lower limit is to 20.0 and 20.8, so you have about 0.2. Okay, we're dealing with millimeter because you see the 0 right in front of the decimal. Yeah, so I know that I'm not in inches, I'm in millimeters, so 0.2 millimeters. Yeah, so that's your flat plane right there for primary datum. And this is your tolerance, and you can vary in between 0.2 millimeters for that. So this parallelism is your R, okay, looking at this surface and then that surface, okay? And here is 0.4 millimeter, see? Meaning like that two surfaces got a parallel, to each other, 0.4 millimeter. That's kind of like your tolerance. It's got to be within that. Yeah. So here, we have, this is your flatness. Yes. So that's a 0.2 right there. And here, this dimension is you can vary in between 0.8. Okay. Okay. So that's all about what you need to know. You have three things going on. Your control frames right here, okay? Datum reference. You have parallelism between the surface and that, okay? And it's got to be within 0.4. We're in millimeter system because you have a 0 is written in front of your decimal, okay? So just by looking at the values, you know that you're in millimeters. We're not reading any of this, okay? You have to learn how to read your drawing or someone else's drawing, okay? Single primary datum is right here, okay? Two things going on. The surface, flatness, your tolerance 0.2, because it said it so. This is controlling that. And it's showing you, hey, I am controlling this. Hey, I am controlling that, okay? Since this is a flatness, that is a surface single. This is a parallelism, so therefore you have two surfaces because you can parallel with only one surface, yeah? Your datum, okay? Another tolerance is right here, and that's your tolerance size is 0.8. All you have to do is just minus that, okay? Okay, then we get into another one, yeah? And here your part is exaggerated. So since we're exaggerated, we can be able to see the details of it. Yeah, since we're looking at this regularly, so it looks like pretty perfect. When you expand and exaggerate it so big, yeah, we start to see the imperfections right there. So the parallelism, your flatness right there, we start to see, yeah, the roughness, yes, after exaggeration, of course, and that's your datum feature, yeah, because here you have your datum feature completely, yeah, pinpointing the surface. So that's your datum feature symbol right here, looking at this surface in a very, very big way. Okay, so you can see the surface isn't that perfect in reality. Okay, and this one is the parallel feature of that datum because the surface is parallel to that surface. Yeah, so when we say formally datum feature, the surface is parallel to that, so therefore parallel feature. Okay, now we're going to bring our gauge. Yes, we call it simulated datum. In physical world, it is going to be a tool. Okay, stick it into there and you're going to get your datum plane. Your datum plane is what is it? That's just a contact point in between that surface. Okay, surfaces. Again, why do we have to do it? Because that's imaginary. Physically, if you don't have a simulated, okay, datum, in real life, physical thing is a block, which is gauge, we call it. You know, it's just a tool, it's just a little block. Okay, because without that, we can't be able to get the contact, plane. If you remove this, all you have is that. What is that? Physically, it's just your part. Yes, and this doesn't exist. But we imagine that there is a line in between that two, which is the plane. Okay, we call it plane because these are not two-dimensional; they're all three-dimensional, objects outside in the real world. So that's got to be a plane. So therefore, we call it plane. It has a name, and that's D. Okay. And we call that the datum simulator, or simulated datum. Now, since this is exaggerated of that, we can be able to see the flatness right now, So see, that's got to be in between, and it's not that flat. So 0.2 is your tolerance zone. It can vary in between them as long as they stay inside acceptable, for this example, of course. Then we're going to call another one, which is your parallelism. It's got to stay within 0.4 tolerance zone. Yeah, so the surface got to stay in between that little two, lines. And that's acceptable for verification purposes. Yeah. I'm going to go back. And you don't have to worry about that because that's just talking about, for this part, okay? And for datum is we are dealing only with this, okay? Alright, so done with that example. It's not that bad, it's just too many slides because it's showing you on one step after another. Okay, this is reiterated again. I hate this, alright, slides outlining the truth. But okay, whatever, let's finish this. He's also like writing the same thing again and again. So anyway, so if you have like a single datum, that's really sufficient for verification because our example here has a single datum right there, But you can of course verify go back here, two things that you need to verify for the parallel data zone, and the other one is your flatness data zone. That's what it's talking about, okay? And then of course your primary datum, because you have a single datum, so therefore there's only one. So primary datum is going to give you the attitude of that part. Attitude of that part means what the part has got to be, okay, for the measurement and also the assembly. Okay, so let's take a look at the verification. So now we are verifying this and verifying that. So verifying the measurement with a Zeiss limit. This is our datum plane. So here is our single data. It's going to verify this, and that's just showing you because we call it the Zeiss limit from here to here. From here to here, the Zeiss limit of that part, okay, is in between the surface and that surface. Because the top surface is controlled relative to that datum plane right there. Why it's got to be relative? Because we're dealing with the parallelism, so therefore you need two surfaces. And of course, so you have about a 3-point contact between your datum feature, which is this guy, and then your simulated datum. So what are we verifying? We are verifying the top surface, yeah? We are verifying from the surface plate, which is this guy, yeah? And gauge right there, which is your datum simulator. So again, this is all repeated, yeah, the last one. So the datum plane is simulated by machine elements or gauges. I have already shown you that so many times. Yeah, physically you need it, because without that you can be able to see the contact between the two surfaces to be able to realize the plane in between them. Yeah, because it's so imaginary. And of course, the measurement from that datum plane is always perpendicular, yeah, to the plane. All right. Okay, so in order for us to verify the measurement within the size limit, you're going to use a tool, yeah, called height gauge. And by using that tool, you can be able to verify, yeah, the measurement from that gauge surface, because it is usually perpendicular, yeah, to the surface. Another thing, repeated again, yeah. So when we were studying the parts for the parallelism and the flatness, yeah, we talked about the contact points got to be at least 3 points, yeah. So I can go back here, so you can choose the 3 highest, yeah, points in there. And so that's what we're talking about here for the geometric tolerances when you measure, okay. You need about at least 3 points on the datum feature, yeah. Got to be in contact with your datum plane or simulated, yeah. Physically as a gauge outside. All right. Now we'll get into datum precedence. Datum references, if you have like multiple references, you have to think about the order. How are you going to do it? Yeah. So the order of precedence is very important when you deal with the multiple datum references. That's because in order for us to position a part properly and also repeatedly, yeah, in your datum reference frame, you are gonna put your datum features in order, and that order got to go with your functional design significance. All right, so here is your key point. You're gonna order, if you have multiple datum references in your datum reference frame, not only single data but 2 or 3, yeah, at that time you have to put them in the significance, yeah. That significance is your functional design significance, and we call that precedence the order of datum precedence. Which one comes more important, yeah, depends on the function. So symbol, how are we going to put the order? You're going to put it like from left to right. So go from left is more precedent than the right, meaning like more important than the right. Depends on, again, the functional design, okay. Where are you going to see left and right in your feature control frame? The little one row table, yeah. And the very first datum reference is always the primary datum, yeah. Of course, the location of that primary datum is different on your part, yeah. The primary is more important, okay. And you will decide which location is primary in your design by looking at the function of the design, okay. Sometimes single is fine, sometimes you have to use 2 or more datum references. So at that time, you're going to choose which one is going to be primary. Primary is followed by secondary. Which one is going to be secondary on your part? Choose that, and that secondary is going to be followed by primary. So you go primary, secondary, and tertiary, yeah. The symbol is always ABC, but where are you going to put that is going to be, yes. ABC means I'm just saying it, whatever. It can be any letters, by the way, but it's got to go from left to right in your frame, yeah. And left is more important, and of course where that these datum features are going to be depends on the function of the design, okay. All right. So now after you finish, putting in order primary, secondary, tertiary, we're going to give the number of the contact. So primary, you need 3, secondary 2, and then tertiary 1. I've already talked about that, in the initial slides. So if I ask you how many data points, yeah, or how many contact points do I need for primary, datum is 3. For secondary, 2 contacts, and tertiary, a single contact, yeah. So this is how you locate the datum. You can put the primary like wherever in the part. You have to have at least 3 contacts in the part. What are the contacts are between the surfaces, okay? So if you have only 2 contacts and you call that the primary, then you are wrong, yeah? I'm not very strict in grading in this class because you are in the introduction class. But of course, as you go up, and also when you work, these are the checkpoints, okay? And you keep giving like a wrong thing, of course, so you get fired out. So primary datum feature is going to be related to the datum reference frame, yeah? And you're going to have a 3 point of contacts. What other point of contacts, meaning like their contact right in your part, okay? With other, yes, features. And where exactly that is going to be the datum feature, okay, with your primary datum plane, which is your simulated plane. Then you need 2 points on the secondary datum feature brought into contact with the secondary datum plane. So the points gotta go and be in connection with that datum plane. 3 points gotta be in connection with that primary datum plane. And then 1 point got to be in contact with the tertiary datum plane. Okay, so let's take a look at it in this example. So our dimension, and when you look at the control frame right there, we're dealing with 1, 2, 3, yeah. Datum features right there, A, B, and C. When you locate it, you're gonna see the primary is right there, okay. And that's your the front, and then that's your top view, okay. So since this is the front, right, it's gonna be down there. You can see it from the top view for A, yeah. So the surface is right there, and it has 1, 2, and 3 contacts, yeah, with the part, of course. And then for B is right here, yeah, on the on this side surface right there, and it's gonna have a 2, yeah, contact. And then your C is gonna be the back surface right there, yeah, and it's gonna be 1 contact. Of course, datum A is your primary, so therefore it's gonna control the attitude of your axis, yeah, of your holes right there. Axes are where the 2 surfaces cross to each other. The rotation axis, don't forget that. So the primary datum A is going to control your feature, yeah, attitude. Meaning like what's going to be this part is how it's going to be located, how it's going to be oriented, yeah, and all the measurements, of course, are going to be measured from this, as well as from that and that. And here we are dealing with, look at this, yeah, leader right here is talking about the 2, see, of this 2 diameters right there, okay, and you can be able to see that tolerance, okay, right here. So these datums A, B, and C are going to deal with that, all right, dimension. So the measurement, and then we have parallelism and your flatness of the surface, and parallelism of this 2, yeah, the front and then the back of the surfaces. So also controlled by C here, and this one is a flatness of that surface, yeah? A single control right there. Of course, here your control frame in ABC, yeah, and here is your diameter, okay, and you have 3, of course, points of contact for that, yeah, plane with your simulated datum. Of course, for the secondary datum B, you have 2 points, yeah, 2 points contact. Sometimes you have issue trying to locate these points, and you think so hard. Don't think so hard. It's just right there on that plane, okay? Connected to that part on that surface. You can choose any 2 point, yeah? I usually say like in contact because see this plane and that plane is in contact, so I just take that as a 1 point, yeah? And another one is going to come with a tertiary datum, so that's 2 points, and the surface is set with the 3rd one, so that's how I take for the primary. So the surface is set for the second on this surface, yeah, you can see it from this view, And of course, and then the other one is you can choose the one at this corner that's connected to that. This plane and that plane is connected on that line anyway, so you can choose the one, yeah, on that line. We can see that line over there. There's a hidden line right over there. So as long as they're all on the surface, yeah, you don't necessarily choose the 2 points in the middle part. Yeah, if you choose the 2 points in the middle part, that would be just a contact with the bottom surface. Yeah, you can also choose the point on the edge of it. So on the edge, you're connected to the second datum or the tertiary datum. Okay, so this is how you take it. Yeah, so use your brain. You really need brain vision instead of eye vision. Yeah, brain vision is inside that you can see with your intelligence. Eye vision is outside that you see, yeah, whatever that's going on outside. And sometimes you can see it, so you have to see it inside of your thoughts. Yeah, so make sure you practice when you study. Okay, and then we come to, of course, the tertiary. So this is what I'm talking about. So this is 1 point, that's 2 points, and then surface is the third point for A. Surface is the first point, and then the point on the surface, I should say, and then the one that is connected to the edge, yeah, or along that line is second point. And for the tertiary, you can just count the point on the surface because you have already counted this, yeah, with A and also with the secondary, so you don't have to repeat again. Okay. If you want to go instead of the frame, I would just say like point to A itself, point A is related to B, and point A is related to C point. So 3 points for A, B 2 points for B because point B on itself, and point that is related to C. And there is a point on C itself. Okay, so that's how we take the contact points. All right, then we're gonna review the same thing, talking about it, your surfaces or your features. Yeah, we're gonna identify by using primary, secondary, tertiary datum features. Of course, the wording is going to get you some time, but just get used to it. Okay. And of course, they should have like a significant relationship in your design and the function. Every product has a function, what it will do after you build it, and we're talking about that function, and we're talking about the product design itself. Yeah, and we use these primary, secondary, tertiary datum features to verify the dimension. Right, integrity means the dimension got to be correct. Okay, when you build and when you draw. And also we want to know the orientation and location. Yeah, so therefore we measure from them. So all the dimension related to your datum reference frame, you're going to put it in a special note, yeah? And you can verify, you will measure it from the datum reference frame, of course. The origin of that dimension, yeah, got to be on that datum plane because you're measuring from it. And again, all the planes are perpendicular to each other, so therefore your measurement also got to be perpendicular on these planes when you measure from it. Again, order. Okay, so if you use the more than one datum feature, then you got to follow the order. The order depends on the functional design. Okay, and your left is more significant. Yes, all the way to your right. So primary is more significant than the tertiary is in the secondary and tertiary. Okay, so and so. Datums, they're theoretical. They're perfect. All right. In reality, is the opposite of that. Yeah. Datum, again, they are points or planes or axes. Yeah. Or lines. And they're going to, of course, represent your true or geometric counterpart, which is your actual features. Datums, again, they're theoretical, so they do not exist. So in order for us to visualize it, we gotta use a gauge step. Yeah. Again, your design concept, your production processes, your verification methods, all of them are based on theory. The datum do exist because we are measuring from it, verifying from it, using it to locate and orient in the space. Okay. Of course, you can simulate them even though they don't exist physically. We can make that happen by using another object, usually the tools, precision gauges. Okay. we can also use inspection equipment, okay, to get that measurement from these planes or points or axes or lines. Yeah, this is just repeated. We use a simulated datum. Simulated datum in real life is some kind of equipment, yeah, gauge control surfaces, to establish the datum that we theoretically use. Alright, then we come into implied datum and datum precedence. So implied datum is nothing, it's just a surface feature, yeah, and we can identify that by its row, okay, dominant row. What kind of a row is just a dimensioning technique or method. And you all know that we use a datum to measure, okay? So it's just dealing with your values or dimensions, yeah, specifications. Since we are measuring, of course, we call that dimensioning technique or method, yeah, implied datum. It's just a surface feature. So in real life, it's a baseline dimensioning. You're going to hear that all the time, that method, and that is an example of your implied datum. Right now, you can get it, okay? So just listen to it for now. So what is this method? We use one or two surfaces, yeah, to control the origins of all other locating dimensions or features on a part. Because why do we need the locations, yeah, and orientation? Because in order for us to be able to understand that part, yeah, every dimension of the features in that part are very important, yeah. So for us to measure them, you got to use a datum, yeah, and one of them is your implied datum, and that's nothing but your baseline dimensioning, yeah, fundamental dimensioning. So all dimensions originate or refer to the baseline. Yeah, we go by this implied datum method. So baseline is pretty good, you know, even though that baseline is not designated as your datum feature. We gotta know that all other features on that part, okay, are related or linked to it, okay, directly or indirectly linked to that baseline. That's what we call it, baseline. Okay, so we use the implied datums for non-critical, yeah, and also very important feature locations or relations. And then you can imply the datums by location dimensions, yeah, associate with the specific features on your part. And your precedence is important. And so we're gonna use a appropriate notation and symbolism to identify the precedence order, yeah, priority or importance order. In your datum precedence, you cannot imply it, yeah, even though the name is implied. Of course, precedence is order, and it depends on the significance, yeah, functional. Okay, so baseline dimensioning example. So we have this part right there. You have views, yeah, 3 views right here. You have 2 holes right there. You can be able to see all of them anyways. We have a little section right there. And so when you look at it, we know that we're in implied method because baseline dimensioning, just by looking at it, baseline dimensioning is used. So we're gonna go, our first view is your top view, yeah, and you're gonna go to the lower right corner, which is this, yeah, and that is your index point. What are we locating? We're locating the feature. So what are the feature? We can see right there, yeah, right here too. So right there is your hole, yeah. And why do we need to locate the feature? Because we have to measure from that datum, yeah, implied datum. So we can be able to get the depth and the width of that object. And we're going to see how we're going to do the primary, secondary, and the tertiary datum features. So let's take it here. Now we're going to look for the significance, because in order for us to come up with the primary, you have to find where is the most important thing. That is, So we're going to start assuming presuming that the orientation of the whole axis, is significant because we have two holes right there. So for this part, these two holes are significant, So we definitely like to assign either the top, or the bottom of the primary datum. But we gotta understand, since we have a top and a bottom, surfaces, we have to know like which one is the primary datum. Is that the top surface or is that the bottom surface, in order to deal with these holes functionally, which are important. And then a location of these holes is so important. Here we can see all the dimensions showing that where these features are on that part. So we gotta think about where we're gonna put the secondary or tertiary. Okay, so secondary and tertiary are the ones that you are going to measure, these holes from. So since we have a 3 touch point, we will choose the bottom surface as your datum A. And then we have holes, so therefore we're going to choose, the datum B is going to be the secondary datum, which is this, on the side. And then we're going to choose, datum C on the back, or front, of course. Sorry, yes, on the front. Sorry, because the holes are on this side, not on the back. So that's how we'll be choosing, the bottom, the front surface, and the side surface. Bottom surface is your primary datum A, the side is your secondary datum B, and the front surface is the datum C. Okay. All right. Specified datum is different from implied. So here we have another example, and here in this example, you can be able to see. Okay, it looks like the same thing to me, but the only difference, the same part, of course, the only difference is that you have specify, so therefore you have control frames right there. Specify means, hey, I'm controlling this, and that. It's telling you, hey, I have a 3 datum features which is going to control that, and I have a 1 datum feature which is going to control this flatness, and I have a a 1 datum feature which is going to control the 2 surfaces. Okay, so datums A, B, and C clearly, right here, identified by your datum feature symbols. Right there, and then right here. So this surface and that side surface, and then this one at the back, actually, not the front. And not like in the implied. And then we're gonna come, and showing you where these primary datum is on the bottom. And then, of course, you have a secondary on the side. The only difference with the imply here in the specify, the datum C, is going to be on the back surface, because it's said so here anyway. For here it didn't say anything, so you can assume it. Okay. Review. So datum reference frame, again, they are theoretical, not physical, and they don't exist. Since they're theoretical and not physical, they do not exist. Where on the part, of course, your actual part features got to be brought in contact with your simulated datum, in order for us to be able to realize that a datum reference feature. So your theoretical data reference frame, is going to represent your feature, part feature. Review again. So your datum simulation process, we're going to put the datum simulator, with the datum feature, and then you're going to specify the order. So the precedent depends on the functional design. And of course, that's a repeatable procedure. Again, what we do all that for is for the dimensional verification, because it's important that your manufactured part is exactly what you as accurate as you have drawn. Okay. So therefore, your fits are correct. Your parts are going to join and mate in an appropriate way, and you won't have a lot of defects. or 0 defects. I'll go with 0 defects. Okay, the next one we'll get into interrelated datum reference frame. So we have a standalone datum reference frame. We have already seen a couple of examples, and right now we'll get into interrelated ones. So it depends on, and interrelated datum reference frames are there because your design is not always simple. It's sometimes very complex. So the complexity and the functional design requirements are very important. Depending on that, you have one or more datum reference frames. Of course, we need these frames to control and also verify the features or the finished geometry of that part. So if you have like a change in the order of the datum precedence or material condition, you will have to come up with the different inspection methods. If you come up with the different inspection methods, you will have to have a different reference frame. You need the reference frame to do the inspection, And that method again depends on the datum precedence and also your material condition, okay? So what are the material of your part, all right? The part. We don't really have the limit to the datum reference frame, so you can use as many as you need in your part. But when you assign the character or letters, you can only use once, okay? You can do like 2 A's or 2 D's or 2 C's. And it doesn't have to be ABC all the time, So I have a 2 feature control frames right there. And we have a surface angle, is what we're looking at with datum A and B. So this datum A and B is going to control that surface angle, So we select the surface angle. But it is interrelated, with the angularity. So here you can see, so here you can see this little symbol right there that's talking about the angularity, And this is the angularity geometric tolerance, and this is your A and B is your control, okay? Then we'll go to the second frame, which is 2 holes right there, because you can see this arrow, leader. So we'll have 2 of them, yes. And you can see right here that diameter is controlled by A, B, and C right there. So this is the same part, right? So you have 2 different views right there, and you can see that they're interrelated. See your A here and here, your B is here and here, and then of course your C is right there. So for the attitude of the whole, which is this one, right there, auxiliary view, you can be able to see that with 45 degree. Don't forget it on the views, please. Oh my gosh. I don't want to think about it. So that's the next, the third, control frame right there, and your primary is going to be the sky right here, and it's going to be controlling this little circle right here, and tolerance is 0.2 within. We need a max, max material condition, and here also max material condition for that circle right here holds. Okay. And then the next one is this little one, which is the second one, It's going to be 2 of them on this side and on this side. So you can see, of course, here you can see. And that will be controlled by the same D, And another new datum feature is E, okay, with the maximum material condition right there. So when you take a look at it, and that is going to be right here, I put it on the control frame, because it's difficult for you to put in this view. So that's just attached to there, So you know that it is right here, referring to that little circle right there. And what it's talking about this is it is associated to this hole as well, So you have 2 different holes. So therefore, is you will have to when you do this E datum feature, you have to think about this too, okay? Because you have a location of the 2 associated outside holes, and that's happening on the surface, on the same surface, and that's what we call interrelated datum. Yeah, it is a little bit difficult for you to be able to see, so please take time to actually look at it. Okay, you'll have a little bit of confusion. So why? Because of the way the datums are put in different views. Yeah, so you know that. So I want to tell you, yeah, this little, yeah, angle right there, you have a surface, yes, A, and then look at this. So this is, you have to think about what view you're looking at. Okay, and so this view is actually looking that way. Okay, and this one is that. Okay, so very different, by the way, two different holes right there. So you're looking at, your eyesight is like this. Okay, so if this is a front view, that is actually bottom, yeah, looking from the that way. So be very careful with your 6 different views. Okay, this problem is a little bit tricky for you. So what I suggest is, I did ask you in the beginning of this semester who can do the AutoCAD, yeah, and also the SolidWorks. You have about 10 months. Yeah, if you started MET 101 or 121 last year, then you have about 10 months. Yeah, and if you were in my class, I told you, I gave you the access to the YouTube videos. Yeah, perpetually. So you gotta go back and study that. You have to. Okay, you don't leave it. It's not like a 1 semester thing. Application is forever. So therefore, yes, please build, yeah, as much as you can. Go back. Don't throw out your textbook. Don't sell it. You need it. Okay, and keep doing it. And you have to build this one in the application. Okay, so when you build it, you can see, okay, your isometric views. So in that way, you can be able to locate the datum features. Okay, like that. So make sure you do that at your home when you have time. Okay, don't be lazy to study. Study needs an incredible amount of concentration. Yes, and also activity. You have to do it. If you don't do it, it's impossible. Doing mean like drawing with your hand, playing with the application. Right now we have a powerful application to play with it, draw with it. Okay, use your time to build these things in your application so you can visualize, yeah, easily. Don't just waiting for the professor to do everything for you. Okay, so build that, and you can see the surface and that surface all together. Yeah, for us is we're doing it all the time, so we can be able to see it in our brain. Okay, so for you, you can see it in your brain right away. So therefore, you still have to build your models and use your application to do that. Yeah, so when you get your ISO, then you can be able to see, you know, by turning around your mouse, yeah, in your application to see all different views. Yeah, so you can realize the surfaces. Yeah, so that way you can be able to understand how these control frames are controlling each of this, yeah, tolerance given to you related to these features, yeah, on that part. Okay, then we're going to get into your temporary and also permanent datums. So temporary datums, they are just the surfaces or features on the part, yeah, like your castings or forgings. These are just machining, by the way, making the parts. But it's called temporary because you're going to remove them or modifying them, yeah, with more machining processes or operations in the production process, of course. So if you still need more machining, then we call them temporary datum, yeah. Of course, a temporary datum, people don't want it, yeah, that much. We want to deal with the permanent datums more than the temporary one because it's a lot of work. But of course, some industry is necessary and depends on the product, how important that is, yeah. So if it is needed, do it. If you don't need it, don't waste your time on it. Permanent is these features, they don't change, yeah, in your production process. All right, the next one is a primary internal datum with your RFS. Your RFS is a review, yeah, so that's for your datum feature of sites. And we know that your datum is going to be realized by the actual contact of the feature surface, your high points in between the two surfaces, your surface of the datum feature, and also the tool or your simulated datum, which is your gauge physical outside or processing equipment of some kind. But this is we have already talked about it. Like gauge, like your chuck, your mandrel, or vice, or centering device, are all gauges. They are variable gauges that we use. So why do we use it? Because we want to see where the datum axis or central plane is. Okay. So the simulated datum for the feature with your RFS, okay, datum feature of size is your center plane of that gauge, okay. So the center plane is again, what is it? That's your feature's true geometric counterpart. That's your actual mating, okay, envelope. So again, you should know by now, every time we think about the datum, they're always on the surfaces, And sometimes we use the point and line, but most of the time a plane, yes, because you have a body for the part that you're building, body meaning in 3 dimensions, so therefore most of them are planes, datum planes. And of course, what do we do with the parts? You don't just leave the part alone, you assemble them. So therefore that's where the mating envelope comes from, okay. So make sure you keep your common sense when you're reading. So center plane, that's the center. Every time you talk about center, you're dealing with 2 things. So therefore you have 2 parallel planes, And usually parallel is because we know that all the planes are 90 degrees or normal to each other most of the time, unless you have inclined surfaces or oblique surfaces with angle. Again, the same thing as we establish the datum plane. So you have to have a high point, so where your contact points are. So let's take a look at it in picture so that you get a better understanding of it. So here is the part and your simulated datum for that RFS. Your datum feature of size, okay, is going to be the center plane of the gauge, okay, representing your true geometric counterpart. So here is a little better way to be able to see that. Here is your datum, So this is what we're talking about, the center plane, And don't worry about the true geometric counterpart and things like that. That's where the gauge is going to come in. That's what it's talking about outside, okay, in real life. And so this and this is your datum simulator, okay. It's going to come in contact with that. So basically, we're looking at this line right there, okay, right here, and that's your center plane. Why do we say it? Because of this datum, If this datum is somewhere else, then the center plane is going to change. Right now, your datum is showing you from here to here, so the center is right there, okay? So since you have a center, you have 2 lines that you measure the center from, and that 2 lines got to be at maximum separation, yes? Of course, for this part, there's a groove. So we're talking about, that's got to be the maximum separation from each other. Why does it have to be the maximum separation? Because we're looking at the high points of the opposite surfaces, the highest point, okay? And the center plane is going to be your data center plane B in this case, okay? All right, then we'll get into primary external datum width. Just a measurement, a lot of measurement. So now we have datum A in this case. So we got to establish the external feature. So let's take a look at. We have to bring it to parallel planes, and it's got to be minimum separation. Why? Because we are dealing with the external feature. If you have an internal, it's got to be the maximum separation. So let's take a look at it. So here we have a datum simulator right there with the blue thing that we draw. And you have your datum feature A is going to be right here. And this is your datum plane A, of course, and that's your center plane, and where the gauge is going to be. And of course, that separation got to be the smallest in order for us to get the external, again, the external surface. because we want to establish the external feature. Yeah. If you want external feature, then this gap got to be the smallest. Internal, that gap got to be the maximum. So why do we have to be like that? External surfaces, and it's got to be the smallest, separation of the parallel planes. Because your true geometric counterpart, because it's got to be the true geometric counterpart of that datum feature. That's why. So just remember the counterpart, the other one, okay, not the one. So therefore, if you think about the external, it's got to be the smallest separation. Okay. And again, you can be able to see it, so don't attempt it. Don't attempt it in your brain. I would suggest you build, okay, build, and build it in your application to be able to see that. And this is the intelligent things. Sometimes you can't be able to draw it to see it. Yeah. Your brain most likely is going to get the external surfaces, so therefore I might have the biggest separation between the two. That's what you would think, but no, it's always very tricky. Okay, and GD&T is very, very tricky. That's why so many people lose their job and think the opposite of what you actually think. Okay, usually you will get correct. So it's because we're dealing with, it's got to be the counterpart of your datum A. So therefore, what's real, you have to get the opposite of that. Okay? All right. trick, and trick. Primary external datum diameter. So let's take a look at it. And now we're going to get into, in this case, is a diameter, and we have a datum plane right here at A. Okay? And here, of course, we're dealing with the axis. So simulated datum, your external diameter, external diameter right here, and your axis of a variable gauge is going to be right here, and that's got to be in physical contact with the high points of your datum feature. So if I say datum feature, you know that we're talking about here, since we're dealing with the external counterpart, so therefore it's got to be the smallest, circumscribed or cylinder right in there. And that's got to be in contact with your high points of your surface feature. Okay, your high point surface is right there. High point, when you exaggerate it, you're going to see the imperfection of the surface and bring the high points on these roughness on the surface. Okay, and you will be choosing the counterpart, which is the smallest circumscribed cylinder. Brought into contact with that thing. Okay. Then we're going to get into here. Now we're going to put the gauge. So this little part right there, which is yellow or kind of orangish yellow, is going to be your variable cylinder gauge. So I'm going to put that cylinder into that gauge. So when you put it, since this is so perfect, your cylinder that you saw, what looks like perfect, is going to have some imperfection on the surface. Right, your datum axis is going to be A, which is this guy here, in two-dimensional perfect picture. This is gauging and measuring that datum feature A right there. So the axis of the true geometric counterpart, which is your gauge right here. So that gauge is going to contract around the object, and it's going to make in contact with the high points of the surface. High point mean here we have an exaggerated picture, so you can see the high point in contact with that gauge. We're talking about that. So the gauge axis is going to be your datum axis. Okay. And here, of course, your smaller circumscribed cylinder. And that's going to brought in contact with the high points of the surface, feature surface, which is this one right there. Okay, if you forget about it, what are we doing? All that, or I'm not getting it. We're just establishing the datum axis, which is this guy, and that's of course we're measuring from the surface. And since you have to establish this, we always bring a gauge physically, yeah, to measure from, because you can't just measure from the surface of the cylinder itself. Yes, because our datum axis is right in the center of it. So therefore, you need this distance and that distance in order for us to be able to get that center. Yeah. So therefore, since this blue thing is imperfect or perfect, we don't know. We need to measure it against, yeah, the gauge. So that's what we're doing. So when you measure against the gauge, this measurement from here, yeah, from here to the gauge, from there to the gauge, that's your datum axis reference axis that you measure from, got to have almost the same, yeah. So that would be the center of it because that's the axis. So anyway, so the measurements are done that way, yeah. Since you measure the gauge, it's the same as you measuring that surface, yeah, like that. So in real life, because you have a datum axis right there, and every point on that surface on the blue, cylinder is going to be measured that way to verify, yeah. And you bring all of your tolerance variable zones right in there to measure with. Okay, so primary internet datum diameter. I don't want you to think too much, all right? I want you to take it as it is. Don't get into the difficulty of the wording, yeah? A lot of terms, technical terms that is getting you because they're not common terms that you use every day with your language or whatever, yeah? And it is very difficult in the beginning, yeah? Even to pronounce it or get it in your head. Even the native speaker don't get it right away, okay? So whatever that is, you have technical terms that you need to familiarize, and it is hard and difficult in the beginning, but don't worry about it. As you read it again and again, as you draw in your application again and again, look at it again and again. If you're fortunate, then you already have a job and you do it, again and again, experience it, accumulate your experience, with the parts that you're drawing or verifying, you will get them, okay? If you don't have anything or no job, then just read, okay? Academically, we're studying, studying with a book knowledge. People will say, but don't worry about it. Same as book knowledge, it seems experience outside, yeah? Even better actually, because you're using your brain to see through the things that you don't even have access to, okay? So if you do it right, it's more valuable actually, yeah. You've got experience, you do it the same thing daily, so you're skillful at it, but then you lack the complete knowledge of it. So you will, when you go to work, you're going to see those kind of things, all right, with your colleague or co-workers. Sometimes you may have more knowledge, but you might not have experience. But knowledge is always, to me, in my opinion, always better than experience, because the more you know, yes, the stronger, the stronger your skills are going to be. And you can quickly pick up, by the way, if you know it right. If you don't know it right and you're delusional as if you know, then of course you're going to fail to be able to do it. So this also depends on whether you can be able to apply the knowledge you've got or not, right? So it's not that easy. I know that everybody have access to education, everybody want to be educated, but I hate to tell you that in real life about 80% failed to apply that knowledge, okay? I hate to tell you that. However, the 80% can be trained to do the same thing, so that's the reason why 20% become supervisors and go up, and 80% still in the workforce, okay? So anyway, let's just make sure that you read again and again to get these technical terms, all right, into your knowledge and brain. Okay, so this is another diagram right here. I'm showing you the part right there, and we can see the simulated data, and here is your axis, and that's your variable gauge right there, and it is in physical contact, with the high points of your datum feature. Again, even though the axis is right here, yeah, the datum A is right here on that, yeah, and this is your dimension from here to here, the separation between the two surfaces of that part. Since we're dealing with the internal diameter, yeah, it's got to be, the counterpart is going to be the largest inscribed, yeah, cylinder. So internal diameter counterpart is the largest inscribed cylinder, yeah, brought into contact with the high points of your feature surface, which is this guy right there. And I'm telling you again, don't try to force yourself to relate the internal diameter and the largest inscribed. We're talking about this is the inscribed inside your cylinder. Because since this is a cylinder, your gauge, even though we're showing the 2-dimension, yeah, 3-dimension is going to be like the cylinder inside of the gauge. Yes? So, and these are the things that you've got to, yes, to be able to vision it in your brain, okay? And make sure you get what you're reading, yeah? Don't just look at the 2-dimensional picture and try to think like the gauge is a block. Yeah. These are the things you need to train yourself to be able to get it. Okay, you're dealing with a cylinder. It's a simulated datum, okay, is for that internal diameter. You're dealing everything with things circled that you can be able to see from the side view. Yeah, from this view. Here is we're seeing a section, which is a cut of the, you're seeing the whole of the cylinder, okay, not the entire thing. Okay, get it? So that's why when you think about the largest inscribed cylinder, you have an issue because your brain has an inertia of what you saw. Okay, because your vision is a 2-dimensional cut, section view, which is making you understand like the gauge is a block kind of thing. Yeah. So in that case, you can't be able to find the surface. But if you see the gauges enclosing the cylinder, you can be able to get that very easily. Okay. So make sure you train your brain to be able to understand what you're reading. Doesn't matter what language you're reading; it's the same thing anyway. Yeah. Okay, then we'll get into exaggerated part. So exaggerated part always show you very, very big view so we can even see the imperfection on that surface. Yeah. Of course, it's going to go, the boundaries, meaning like your tolerance, will come into contact at that time. Yeah. And you will play with these, the surfaces got to be in these tolerance zones, and that's what it's talking about. Yeah. So when your surfaces are imperfect, yeah, we will think about the boundaries, of that size, which we have already studied in other chapters so many times. So to verify the axis of that whole, yeah, your RFS, regardless of feature size, and that's your datum, yeah, feature size. The variable gauge is used to measure the largest inscribed, yeah, cylinder. And because we're still in the internal, yeah, internal diameter, yeah. Okay. So the gauge, yeah, axis, which is this, because the gauge is also a cylinder, by the way, and you're putting the cylinder into the cylinder. So the gauge is used to measure the largest inscribing cylinder, and your gauge axis is going to be your datum axis. So for the surface, the very first example in the beginning when we started it, so for the surface, it's really easy because you can picture the gauge as a block. Yeah, so it's pretty easy to find the plane. But for axis, it's inside of the cylinder, and your gauge is also kind of like a cylinder, and the cylinder is inside of the cylinder. So you have a little bit of issue to find the axis on it. Yeah, so that because you have two axes, your gauge axis, your simulated datum, and the other one is the actual, actual middle point, which is the center of this cylinder, is also your datum axis A. Okay, so give a little bit of time on this to digest that, and I believe that if you spend about 2 to 3 hours, you should get it. Yeah. Alright, let's get into another one. Okay, so here is your datum axis, and that's for the axis of your true geometric counterpart, which is this gauge. Yeah, trying to measure that, and trying to establish, actually I shouldn't say measure, establish the axis. And then of course you have your diameter, which is your true geometric counterpart from here, the surface to that surface. And then your datum feature is A right here, and then your datum feature simulator, of course, is this thing, the variable diameter gauge. Diameter gauge is different from the block gauge. Don't forget the diameter gauge, they're not the same. And you have your largest inscribed cylinder for the internal diameter. For external diameter, you're going to go with the smallest inscribed cylinder for that variable gauge. Because the internal and external diameters are your zones, so in order for us to measure that this part got to be within that zone, we're playing with that gauge. Okay, of course these zones, the surfaces, are measured from this axis, and that's why this axis is your datum, primary datum axis. Again, datum can be a point, an axis, a plane, okay, and a line. Alright, then we will get into the size of a primary or single datum feature. Please bear with me because, like I told you in the beginning of our semester, the 201 has so much material, so you just have to bear with me. And we give you the pocket, a little book, you need it if you want to keep in this line as your career. So make sure you get that book. You cannot just take the course to get the degree, and if you go into work, you will most likely lose your job because you don't know what to do. This needs an incredible amount of study. By the way, you have to study every day, okay? You have to use your application every day, and do not throw away your textbooks, all right? Do not throw away any of your stuff, please. Giving you the open source lectures is for you to go back when you need it, in the future. Okay, so your primary or your single datum feature size, it's going to be controlled by your circularity or cylindricity tolerance. And then of course we look at the size of the true geometric counterpart, and we're going to establish the simulated datum, with the maximum material condition. And when you think about the straightness tolerance, apply to the feature of your sites. And we're going to bring our maximum material condition, for these cases. You can get it right now, so let's get into to take a look at the cylindrical datum features for that. So cylindrical datum feature is always associated with two theoretical perpendicular planes, And of course, since you're dealing with a cylindrical datum feature, your datum axis, is going to be the intersection of that two perpendicular planes. And your datum feature for a cylindrical thing, is your axis, and that is your true geometric counterpart of your datum feature. And that can be simulated by using the vertical, variable, no vertical, I mean variable cylindrical gauge. I've already showed you that in the other example, previous example. And of course we use it. What are we doing with all of this? Is to for inspection process to verify all of your dimensions and the measurements, of your part, because it's important. Otherwise you're going to get all the defects, useless products out there. You don't want that. So the customer won't buy any more from you. You want to make it as perfect as possible, so the function is going to be intact. All right, so let's go into another one. So we have to establish the cylindrical datum feature, and we are going to get into that by using some example. First, on your drawing, we're going to have two theoretical plane, and then we're going to have a center line crossing at the right angles, and the intersection of that planes is going to be your datum axis, It's kind of like trying to find or locate the datum axis by using two planes, So when the two planes are at right angles and they cross each other, we can be able to locate this axis, to establish it. So after you establish it, we're going to use that datum axis as the origin, yeah, for all the dimension for us to measure from. And then we're going to bring in second and third plane to locate or orient, yeah. These planes are again your center lines as in a cylindrical, yeah, datum. Also, we need to do the direction for the measurements in common sense, and in a simplest way to put it, you're gonna find the axis, you're gonna measure from the axis to verify the dimensions on your drawing in your part. Okay, that's all you're doing. Make sure you get that. Now I'll get into a first example right here, and here is your control frame right there, and then your datum is a C and a D right here. So I have my C right there, okay, and then my D is on here, yeah. So I got everything, and that too is going to control this. So which is where I don't know. So you're going to look at this little thing, and you're going to see 1, 2, 3, 4 of them, yeah, at this tolerance, okay. So when you look at this, so you're going to see the horizontal line and the vertical line, yeah. And these are the planes. Yeah, see this little blue line right there. You gotta pay attention. And you're gonna see these planes and they across each other, yeah, at this center right here. So that intersection is gonna be the axis of that plane. Okay? Alright. So if you have a rotation, yeah, of the feature relative to that axis, datum axis, and you have no effect, you know, on the function of the part, the rotation orientation of your second and third plane, yeah, of your datum reference frame is not specified. Don't worry about it, I'll show you one by one, okay? In that case, what you're going to do is you have two datum features as reference, and which are identified in the control feature, yeah, feature control frame, and your primary and then your secondary. This is your feature control frame, C is your primary, and D is your secondary, okay? And we are controlling this thing, okay, which is on diameter 0.2 for the holes at the maximum material condition, okay? So your C will control the orientation of the axis, yeah? And then your D is going to control by locating the datum axis, all right, D. And of course you can rotate because the set is so, yeah. You can rotate it, but you're not gonna get any kind of bad effect. So that means that there won't be of no consequence, yeah. Meaning like this control frame will still be controlling that, yeah, your primary and secondary datum feature won't get affected by rotation. All right. Then we're going to draw it so you can see it, and here is your control frame right there, and your datum feature C is your primary, yes, which is this plane right here, and you're going to establish that, yeah, by having, since this is primary, you have 3 points of contact, yeah, with the datum simulator, which is some sort of equipment to measure that, yeah, or to establish that. Then we're going to plane another one. We're going to put another plane, okay, which is your first reference plane, and that's going to be established through the centers of that two groups right here, yeah. These groups are located opposite to each other, like 180 degrees away from each other in your drawing. So we got our primary data plane C, and we got our first reference plane. Then second one gonna cross the center of that two other group opposite to each other, 180 degrees away from each other. So we have established the two planes, two reference planes and one primary datum plane. Then here is your rotation axis, yeah, here. And that is your datum axis, which is your secondary, yeah, datum D. It's set as so, yeah. And of course you have a symmetrical features right there, here, 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 and here. They're all symmetrical, so the part is symmetrical. So it wouldn't matter, yeah, how the part was rotated. You can rotate about the axis, of course, and it's going to function as it made, yeah, that part to be, because they're all balanced anyway. So the rotation is definitely not an issue, yeah, in this part. So you only need two datum to control the whole location and the orientation, yeah. So these are the holes right there. I'm going to draw in 2D so we can see our holes, hole for them, yeah. Then here's our tolerance zones right there. Then here's your two, yeah, cross reference planes right there. And we have our primary data C, which is here. Don't forget the views. Yeah, this is a top view, and this one is your side view right there. Okay. And we're going to think about the internal feature, your horizontal and vertical center lines. Yeah. The circular hole in the center of that object have the reference plane. Yeah. And they intersect, of course, at that center, and it's showing here, right there. Yeah. Then here's your circle, so tolerance. And this is also a tolerance for that 4 circles right there, holes. Your intersection is going to give you this axis, yeah? And of course your holes are all relative to that axis, okay? Axis can rotate and it's going to affect, yeah, any of the datum features. All right. Now we're going to draw it, a primary datum plane. We can see it. Primary datum C here. You should be able to read the control feature frame, okay? Feature control frame. And then you want to establish that, yeah? Primary datum, which is C. And it's got to come in contact 3, yeah, points. And with what? With your datum simulator, some form of gauge or tool equipment, and you tool it. Okay, your reference frame, another reference frame. They're all again the 90 degree to each other. Each one of them is also 90 to the primary datum. And of course, they're located to opposite to each other too. And pass through the center, and you get the center where the axis is, yeah. And now we throw in the axis at that center point. Okay. So this example is a little bit similar to the circular one, yeah, the one that we just saw. But right now it's more of a square thing. But again, even if your axis is right here, still they're symmetrical, so your rotation isn't an issue, yeah. So 2 datums, again, we only need 2 of them to control this, okay? Or location, which is this, that. And orientation, okay? Location is where they are, orientation, how they're located, how they are staying in the space, okay? All right, rotational orientation. So rotational control the first and second reference plane about an axis in a cylindrical datum reference frame. You can establish by referencing a third or tertiary datum feature. So the tertiary datum is a datum axis or center plane, okay, which is going to be aligned with the primary datum axis and one of the 2 reference planes. Okay, so we can't see it, so let's take a look at the diagram right here so you can be able to see that. So you have the center plane of that groove, yeah, on the right side of your for this part, yeah. the right side of the object is your datum C, so we can easily locate that, which is right here, yeah, and that's gonna be controlling 0.4, okay. Of course, here M is off. So this M is supposed to be right here. I try to put it, but it's too small. This diagram is so make sure, this one is a maximum material condition for that tolerance 0.4, okay, which is actually right here in this, group on the right side of the object. And we have our datum C is going to control that, okay. And the datum C is again interrelated to here, which is this guy right there, which is this little hole, which is symmetric to that over there. And that's your, we have three, okay, primary, secondary, and a tertiary datum right there with B and C, which is right here, which is right here at the maximum material condition. And your B, of course, is going to control this, all right? A feature right here with only single data, which is datum feature A, okay, which is right here. You can be able to see in this view. So when you take a look at it, at least you should be able to, see all these datum points, that you need to deal with. Of course, you also have a D and E right here, which is not, inside of the control frame. So the tolerance is specified, so that's your specified datum, feature. Okay. Then of course I'll come into here, and it's a little bit better for us to be able to see that part on this 2D view. Now we have a 3D view, so you can see the primary datum plane, which is A, which is this guy right there, okay. And then of course this cylinder, I'm going a little bit fast, is right there, and please practice your view so you can be able to see it when I'm going fast. So if you don't study, it would be very difficult for you to be able to follow it, because in your brain it would be very difficult for you to see these views. So anyway, so here I have A, B, and C is going to control, this little, which is that guy right over here, because the set is so, okay, right here, so this is what we're seeing in this, okay. So your datum plane A is established, and we're going to use again, since that's a primary, so you have 3, yes, minimum of 3 high points on the surface, and that got to be simulated with your simulated datum, some kind of a gauge or a tool. All right, then we're going to bring our reference planes. Your first reference plane, a second is going to cut through like that, okay, and here's your axis at the center, which across that 2 planes right there, and that's your datum axis B, which is your secondary datum, and it is established by the intersecting reference plane right there. We found it. And the third one is going to be your tertiary, okay. So we're going to bring in another datum center plane C right there, so that's your second reference plane. This is your first reference plane, okay. So that datum center plane on C got to be perpendicular to the plane A, which is this guy right here, that plane. And it's got to be aligned with the other 2 reference plane, that establish the datum axis B right there. So in this case, we're just bringing this C plane, okay, right here. See that, little one right there. If you cut it here, it's a little bit difficult, and then we just draw it with a dark, line, so you can be able to see that. This plane is your center plane C, which is your second reference plane, by the way. All right, and then here I'm going to stop right there because it's already 2 hours of lecture. Oh my god, it's a very, very heavy material for 201, we are suggesting to break it into 2 courses, but they don't want to do it. So anyway, so the last one here just you just want to understand this rotation, okay? Rotational orientation. You can establish that by identifying these two reference planes, because that's your tertiary datum in your feature control frame, which is your C right here. So the feature control about that tertiary datum center plane C. It's what's the same right here. So now we get your A right there, B, okay, right here, and then your C right here. Alright, that's it for the first part, and we'll get into the second part.